We have another interesting topic under the mathematics of artificial intelligence, and that is about how AI turns noise into art. How AI turns noise into art. So here we want to understand diffusion models from first principles. Understanding how modern generative AI systems such as Stable Diffusion and Midjourney create realistic images by gradually removing random noise. By the end of this lesson, you'll be able to explain why diffusion models were invented, understand forward diffusion, talking about adding noise, and understanding reverse diffusion, that's removing noise, explain the role of neural networks in denoising, understand the mathematical intuition behind diffusion, implement simple diffusion simulations in Python, and explain how stable diffusion generates images from text prompts. So explain why diffusion models outperform GANs in many applications. Now, let's talk about or GNs, right? So the big idea here, imagine someone gives you this image of a cat. Now imagine slowly covering it with random television static. So after enough noise, you then have, the whole picture is covered all over the place. It's just covered like that. So this image has completely disappeared. So now imagine learning how to reverse this process. So you now want to remove the noise one after the other, and starting with the random noise here. So AI actually removes the noise. So you then begin to have blurry shapes. Then you have a rough cut. Then you have a detailed cut. And finally, you have a final image. That is the core idea behind diffusion models. All right. So removing all the noise or everything that is making the cut blurry. So why not generate images directly then? So earlier AI image generators, GANs, for instance, attempted random numbers leading to image. So this is an extremely difficult learning problem. So diffusion models break the problem into many easier steps. Instead of generating everything at once, AI repeatedly asks, can I remove just a tiny amount of noise? Thousands of tiny improvements eventually produce beautiful images. Now, you can see noise as you have a clear picture. Everything that makes the clear picture not clear is noise. Things like light reflection, and all of that, these are noise. So, and that's why most of the times you have a photographer takes a picture, they take it to their studio, and then the picture comes back looking more beautiful than what you would have imagined. So they remove too much of light, they remove darkness, they do all kinds of things, they lighten things up and everything. And that's what AI is doing these days. So let's talk about the forward diffusion process. Forward diffusion gradually destroys information. So forward diffusion is simply adding noise to an image. So forward diffusion gradually destroys information. So you have original image, is small noise is added, more noise is added, even more noise is added until you get pure Gaussian noise. For instance, let X naught represent the original image, right? So after one diffusion, you may have x1 equals square root of 1 over 1 minus beta 1 multiplied by x naught plus square root of beta 1 multiplied by epsilon, where beta controls how much noise is added and epsilon is Gaussian noise. So after many steps, then you have x sub t, follow is normally distributed with mean 0 and standard deviation I, meaning the image becomes almost undistinguishable from random noise like that because you have added so much noise. So visual example, imagine you have this original image like this, and step one, you have some, so the image has become, it has lost some information, and in step 10 you've added some things by the side, and in step 100 you can't even see anything again because there's so much noise, and in step 1000 you see pure random pixels. Now every detail eventually disappears because more and more noise is being added. So here adding noise now, so import number as np math plus lib as pi plus so we can visualize. So imagine you have an image with 100 by 100 zeros, and then the image itself is 30 70 30 70 30 70 equals 1. So and then the noise is this 0.04 image shape, and then noisy, you now have image plus noise. So in this case you have the gray thing. So see what this one looks like now. Am I running that? Let me see. Okay, I'd run it before, but I'm just running it again. So you have the real image and some noise. So we can even go further and add more noise. So repeating many steps. Now, see if you keep adding noise like that. So one noise addition is not enough to completely destroy an image. So maybe just a little bit of light here can still the image can still be fine. But if you have more and more, so one noise addition is not enough to completely destroy an image. Instead, diffusion models repeatedly add amounts of Gaussian noise over hundreds of thousands of time steps. Each step removes little more information until the original image is no longer recognizable. Mathematically, xt is square root of 1 minus bt multiplied by xt minus 1 plus square root of bt epsilon t. So this is like noise now. So where x sub t minus 1 is the image. So this is the image from the previous step. So B sub t is the amount of noise added. So this B sub t is the amount of noise added at step t. So epsilon t is then fresh Gaussian noise. Eventually, x of t is now because is normally distributed, like that, which means the final image is essentially pure random noise. So repeatedly adding noise now to the same thing we had the other time. So if you add more noise, so it even becomes worse than what it used to be. So after repeated noise addition, you then still have something like this. So you have the image, and this is the image itself. Now the current image, so the current image is the copy of the previous image you have, and then you add more noise to it, and you then have something not as maybe this was even a bit better, right? But well, like, you may not see so much difference, but so adding more noise, see what that's led to. Then what happened here is initially the white square is clearly visible, right? So every iteration adds a small amount of random noise. Although each individual step seems insignificant, the cumulative effect gradually overwhelms the original signal. This is exactly the forward diffusion process used during training. So the AI later learns how to reverse this process. It's a kind of training. It's more like you're training a banker to recognize fake notes, right? So that when a fake note comes, so maybe you try to make an original note into a fake note. Maybe that's not a good example. You take a proper picture and make it blurry so that AI can now know how to remove what was added before. So that way, when it now sees a really blurry picture, it can then do the same kind of thing. So that is forward diffusion. Then we can have reverse diffusion. So the remarkable idea behind diffusion models is that they learn to reverse the noisy process. So it has learned how to add noise to a picture to make it blurry. So now you have the image, and then that leads to the noise. That's instead of transforming image to noise, the model then learns to take the noise and extract the image from it. So because it was trained to add noise, so it knows the process of adding the noise, so it can remove the noise now to get image. So this reversal is not achieved by simply undoing the equations. Instead, a deep neural network learns how much noise should be removed at every step. So each denoising step produces a slightly cleaner image. After many iterations, the original object gradually emerges from pure random noise. And that is why you can take a picture that is already blurry, a picture you took like 30 years ago. You can just feed it to ChatGPT or some other AI tool, and then you get a clearer picture like that. So because noise has been removed, all the blurriness has been removed. So during training the neural network now, during training, we already know the clean image, right? So we deliberately corrupt it with random Gaussian noise. So the training pipeline is then this. You have original image, add random noise, then you get the noisy image. Then the neural network receives an input of a noisy image, and its learning target is this. So the target is the exact noise that was added. Then rather than predicting the clean image directly, the model predict the added noise. So this seemingly simple idea turns out to be much easier to learn and produce remarkably high quality images and produces remarkably high quality images. So the learning objective here is suppose x naught is the original image, epsilon is the random Gaussian noise, x sub t is the noisy image after t diffusion steps. The neural network is represented by epsilon sub theta of xt comma t, where theta denotes the network parameters. Then x sub t is the noisy image, and t is the current diffusion step. So the network tries to predict the exact noise that was added. So the loss function then is L of the expected value of the norm of epsilon minus epsilon naught xt comma t all squared. So this is simply the mean squared error between the true noise and the predicted noise. So training continues until the predicted noise closely matches the actual noise. Now the question is, why do we predict noise instead of just going for the picture directly? So a natural question is, why doesn't the neural network predict the clean image directly? Predicting the clean image is surprisingly difficult because images contain highly complex structures, textures, colors, and fine details. So random Gaussian noise however, follows a simple statistical distribution. So since the noise has predictable properties, it is easier for the neural network to estimate. So once the model predicts the noise image can be cleaned by subtracting it. So you then have estimated images, the noisy image minus the predicted noise. So this denoising operation is repeated many times. Each iteration removes a little more noise until a realistic image gradually appears. So, and that's exactly what's happening when you feed it an old picture into AI and you tell it what to do. And if the picture comes out and you don't really like it, you want to say, okay, why not add some light, remove some light or whatever, and then it's doing all of that. Then for reverse diffusion loop now, image generation begins with nothing but random Gaussian noise. So you have random noise, and then you have neural network predicting the noise. And then once the noise is well predicted, subtract the predicted noise, then a slightly cleaner image is obtained, and then predict the remaining noise and subtract again, and then repeat this process many times, and finally get a high quality image. And the whole idea of AI is doing very simple things several times or doing simple things on a lot of data and then become something really serious. So each denoising steps makes only a small improvement, but hundreds of such improvements accumulate into a realistic image. So this gradual refinement is what gives diffusion models their impressive image quality. So of course, we have some examples to play with here. Imagine simple demonstration of iterative denoising. Just a conceptual example, by the way. So you have the image you've been talking about, noise is added, and then the current noise. Now you copy the current noise and you do a simple smoothing based denoising. So that's the process of removing noise now. So imagine you have this. That's conceptual denoising now. Well, you may not have seen a lot of difference between this and what we've been seeing before, but we are going to see as we go on, you are going to see the clarity. So the Python example above is not a real diffusion model. A true diffusion model uses a large deep neural network, typically a U-net, to estimate the noise at every diffusion step. So this simplified example only illustrates the idea that repeated small corrections can gradually recover a cleaner image. So you keep removing noise step by step. Now, what is Gaussian noise? Nearly all modern diffusion models use Gaussian noise because it has simple and well understood statistical properties. Mathematically, noise is normally distributed. It follows normal or Gaussian distribution. The mean is zero, so the zero is here is the mean. So positive and negative noise are equally likely. Then I is the identity covariance matrix. This identity covariance matrix, meaning each pixel receives independent random noise with unit variance. And every pixel is perturbed by a random value drawn from this distribution. So as more Gaussian noise is added, the original image gradually disappears. So imagine now adding, so imagine you now add a random noise of 256 by 256. So still working with the same image like we had before. So if you do this now, you see the image is undistinguishable because so much noise has been added. So it looks like something totally different. That's Gaussian noise. So Gaussian noise has several important advantages. It is easy to generate. It has elegant mathematical properties. It behaves predictably rather under repeated additions. It allows efficient optimization during training. It makes the reverse denoising process mathematically tractable. So for these reasons, Gaussian noise has become the standard choice for diffusion models. Then we have time steps now. So diffusion is not performed in a single step, right? So because it's, just like the whole AI thing, it's doing a little thing over and over again to get a big result. So instead, the image evolves through a sequence of time steps. T is 1, 2 up to T. At each time step, a small amount of noise is added during the forward process, or a small amount of noise is removed during the reverse process. So early denoising steps recover the core structure of the image. The middle steps reconstruct larger objects and shapes. Final steps recover fine details such as textures, edges, lighting, and shadows. So the neural network is also given the current time step t as an input so that it knows how much noise should still be present. Then we have conditional diffusion. So if diffusion starts from random noise alone, the generated image is completely random. So to generate a specific image, you must provide additional information called a condition. So for text to image generation, the condition is the user's prompt. A red sports car parked beside a lake at sunset, right? So the prompt is converted into numerical representations called text embeddings. So during every denoising step, these embeddings guide the neural network toward producing an image that matches the description. So instead of generating any random image, the model now generates one that is consistent with the prompt. So a red sports car. So that's what, if you see ChatGPT generating an image, so it's doing a lot of, so it just starts, okay, let me even do a practical thing now. Let's say, if I let me use this exact word here for ChatGPT, right? So you see, it takes a bit of time before it comes on. So I just come here and I'll come to ChatGPT. Then I just throw in this particular prompt. So I paste that a red car, blah blah blah, kind of thing. So a red sports car parked beside a lake sunset. So I run that now. So once it starts, you can say it's creating image. It's creating image. It doesn't just create it because it's reading now. ChatGPT doesn't understand this grammar here. This a red sports car parked beside a lake at sunset. ChatGPT doesn't understand this English. But once I put the prompt in, the prompt is converted to tokens, at the back end, and then the tokens are embedded, and that embedding now helps because the model has been trained on all kinds of things like this, so it can now pick this. So you can see the beautiful red car it comes up with like that. So because though it does not understand English, but it can convert the English to, to proper to mathematics, and then, return the image by matching as it should be like that. So that's what exactly is happening there. So we have all of that. So a red sports car parked beside a lake at sunset. Red sports car, lake, sunset, like that. And that's so cool. All right, so this prompt is converted into numerical representations called text embeddings. During every denoising step, these embeddings guide the neural network toward producing an image that matches the description. Instead of generating any random image, the model now generates one that is consistent with the prompt. So that's why it takes a bit of time for that to happen. So talking about the text to image pipeline, this complete generation process follows these stages. So immediately I typed in this prompt. You saw a red sports car parked beside a lake at sunset. So there's encoding done, text encoder, text embeddings are done. Then you have random latent noise added. Then repeated denoising by the diffusion model is added. Then you then have latent image decoder, and final high resolution image is produced. So every denoising step is influenced by the text embeddings, allowing the generated image to increasingly resemble the user's description. This is the fundamental pipeline used by modern text to image. So when the prompt was first done, and you can see some, so the first thing you were seeing were some, such a noisy kind of image. So you can see all of this. It makes no sense. So as with the noise happening, so you have a process of denoising going on, removing whatever noise that should be removed. And at the end of the day, we wait a bit and the noising is going on, going on, going on. So you can see the even all the dots, all the pixels moving around the image. So it's making sure it's paying attention to the fine details that should be happening there. So now it has even changed the orientation of this now. So a sports car parked beside a lake at sunset, like that. So sports car, lake, sunset, all of that. Right, so that's what is actually happening. So every denoising step is influenced by the text embeddings, allowing the generated image to increasingly resemble the user's description. This is the fundamental pipeline used by modern text to image diffusion models, such as Stable Diffusion. So now talking about Stable Diffusion, now every diffusion models performed denoising directly on high resolution images. Although effective, this approach required enormous computational resources because every denoising step processed millions of pixels. So Stable Diffusion introduced a much more efficient a much more efficient idea rather. So instead of working on the original image, it works on a compressed representation called a latent space. So you have feature space, that's the actual space, and then that's translated into latent space. That's the space in which the whole AI thing can work better. So the latent space retains the important visual information while greatly reducing the amount of computation required. So the overall pipeline then is this. You have the text prompt, you have the clip text encoder, you have text embeddings, you have random latent noise, you have UNet denoiser, you have clean latent representation, you have variational autoencoder, VAE decoder, and then you have a generated image. Now, because the diffusion process occurs in latent space rather than pixel space, stable diffusion can generate high quality images much faster and with significantly less memory. Then we have the UNet. The heart of diffusion model is a deep neural network called the UNet. Its primary task is to estimate the amount of noise present in the current image. So the UNet has two major components. It has the encoder. The encoder gradually compresses the noisy image while learning increasingly abstract features such as edges, shapes, textures, and object structures. And then you have the decoder. So you have the decoder. The decoder gradually reconstructs the image by predicting and removing noise. So as information flows back through the decoder, the image becomes progressively cleaner. Then you skip connections now. One of the most important innovations in the UNet is the use of skipped connections. So these connections transfer fine image details directly from the encoder to the decoder, right? So without skip connections, many small details will be lost during compression. So this architecture enables the diffusion models to preserve sharp edges, textures, and fine visual details while removing noise. So encoder, decoder, and then skip connections is the basis of the UNet uh, algorithm. Then we have the classifier-free guidance. So even with a prompt, the generated image may not always closely follow the user's instructions. Of course, the only thing is that models have become so good these days that you can almost get something excellent like that. Like it's almost like you took a picture, a real picture of a sports car parked beside a lake at sunset, almost looks like that. Initially, okay, well, maybe when you look at some edges, for if you know sports car properly, you may be able to find some errors, right? Some things that are not quite, up to par. So even with a text prompt, the generated image may not always closely follow the user's instructions. To improve prompt adherence, modern diffusion models such as classifier-free guidance to improve prompt adherence, modern diffusion models use classifier-free guidance, CFG. So the model performs two predictions during each denoising step. You have an unconditional prediction, which ignores the text prompt, and a conditional prediction, which uses the text prompt. So these two predictions are combined using uh, epsilon cap, which is epsilon unconditional plus W multiplied by epsilon text minus epsilon unconditional, like that. So where epsilon unconditional is the unconditional prediction, and epsilon text is the text condition prediction. So it uses the text and uses its own information to make sure we get something better. Then W now is the guidance scale. So it can uh, monitor how everything goes. So when W is equal to 1, the guidance is weak. Larger values of W force the generated image to follow the prompt more closely. However, excessively large guidance values may reduce image diversity and sometimes introduce visual artifacts. So choosing an appropriate guidance scale is therefore an important part of image generation. Then we talk about sampling algorithms now. During image generation, reverse diffusion may be performed hundreds of times. Don't forget, forward diffusion is adding noise. Reverse diffusion is removing noise to get the original image. So different sampling algorithms determine how these denoising steps are carried out. So common samplers include DDPM, DDIM, Euler Ancestral, Hune, LMS, DPM++, UniPC. Although all of these samplers begin with random noise and progressively remove it, they differ in speed, numerical accuracy, image quality, and computational cost. Modern samplers often generate images using only 20 to 50 denoising steps while maintaining excellent visual quality. So choosing a suitable sampler is one of the easiest ways to balance image quality against generation speed. Then why diffusion models work so well now? Diffusion models have become the dominant approach for AI image generation because they produce remarkably realistic and diverse images. Some of their major advantages include stable training. Unlike GANs, let me even remember, I know what GNS are, but I need to remember. Is it generative autoregressive something? Let me see. GANs. GANs. Generative adversarial networks, yeah. So, which are artificial intelligence systems made of two competing neural networks. So, a generator that creates fake data and a discriminator that tries to spot the fakes. So, introduced in 2014 by Ian Goodfellow, they are widely used to create realistic synthetic images, video. So, that seems to follow the same idea of forward diffusion and reverse diffusion. Forward diffusion add noise. That's a distraction. Then remove noise. That's by reverse diffusion. So diffusion models have become the dominant approach for image generation because they produce remarkably realistic and diverse images. Some of their major advantages include stable training. Unlike generative adversarial networks, diffusion models rarely suffer from unstable training or mode collapse. Then high image quality. They can generate highly detailed and photorealistic images like the one I generated here. In fact, if I do the prompt again, we can even get something, each time I rerun it, we get the image comes in a different look still. So you see, this is the process of so noise, then later noise is removed and all of that. And then in a bit, you get a very beautiful, almost maybe what we can call picture perfect image at the end of the day. A red sports car parked beside a lake at sunset. So you have all the maths going on, all the noising, and then denoising, and then you end up getting a a picture like this. So you can see the image looks better now than what we had before. The other one, so that's another thing. So the more you keep get doing it, the more you keep getting a better image. The other time, you can see this edge was somehow bulgy, and it was almost looking like something was not right. So, but now that I've done it again, it has even self-corrected, and that's one thing that also happens in the whole learning thing. So it learns from itself. AI learns from itself. So high image quality, they can generate. Okay, I think I've talked about this. Okay, well, high image quality, they can generate highly detailed and photorealistic images, like I just showed with this one now. Then, excellent diversity, starting from different random noise produces different images, even with the same prompt. So you can see the same prompt has given me three different images so far. So if I even go further and still do it again, we might even get so each one has been somewhat different like that. And that's one advantage of all these things now. So starting from different random noise produces different images, even with the same prompts. Then strong prompt control, like text prompts can precisely guide the generation process. It should be ready by now. I think, okay, it needs a bit more time. A bit more time. Should be almost ready. It's now sketching it out. Sketching it out. Then all the denoising happening in the background. And finally we have it. Yes. So now so it's giving us the back side of the same car and it's looking more realistic than before. So then you have strong prompt control. Text prompts can precisely guide the generation process. For scalability now, diffusion models can be trained on billions of images and scale to very large neural networks. Then flexibility, the same framework can generate images, audio, video, 3D objects, and other forms of data. So these advantages explain why diffusion models have largely replaced generative adversarial networks in modern generative AI. Generative adversarial networks, yeah, in modern generative AI. So the limitations now. Despite their impressive capabilities, their vision models are not perfect. Some important limitations include slow generation. Multiple denoising steps are required before an image is completed. So, as opposed to text, you know, so if I told it to just write me a text, it would just write a text faster than this. Uh, let me just say a poem. Let me just say poem even without even saying anything explicit. I just say poem. So I said poem now. So it starts generating. So you can see the poem is almost ready. So, but if it's image now, it's just a red sports car waits where the shoreline bends. Its polished cuffs catching the day's last fire. The lake lies still, a mirror without end, reflecting skies painted with fading desire. Of course, we know text naturally would require less compute compared to image generation for sure. So, despite their impressive capabilities, the vision models are not perfect. Some important limitations include slow generation. So, multiple denoising steps are required before an image is completed. Then you have high computational cost. Training large diffusion models requires powerful GPUs and massive data sets. So, for you to be able to get this kind of hyper realistic image of a red cap by the lake and all that, so the model must have been trained on things like that. The prompt sensitivity, small wording changes can sometimes produce noticeably different results. So see what we got here now. A red sports car parked beside a lake at at now this is sunset now. Let's say at sunsets. Let's see if that's going to cause any change at all. I'll come back to see that. Then artifacts. Hands, fingers, small text, and complex object relationships may still be imperfect. Now, that's why you see some AI videos, right? Maybe you can see somebody getting into a car, by by walking backwardly into it, or you have somebody standing by a car and they have three hands, things like that. These are artifacts. So fingers, hands, fingers, small text, and complex object relationships may still be imperfect. So that's the kind of thing. But of course, the thing is the models are getting better and better. So now we have it from another angle. So maybe this may not be an unnecessary bend. So here you have number plates. So it's like, it's there's a bit of difference each time, right? Then large storage requirements. Modern diffusion models often require several gigabytes of parameters. So, and of course, if you're training a model like that, you have to get all these things. So, researchers continue to develop faster samplers, better architecture, and more efficient training methods to address these limitations. Then we have applications. Diffusion models have transformed numerous creative and scientific fields. So, for stable diffusion, for instance, you have common applications including text to image generation, image editing, image in painting, image out painting, image to image translation, product visualization, logo and graphic design, digital illustration. These are some applications here. Then you have Midjourney, which is the popular uses include digital artwork. So you have things like digital artwork like this. Okay. Why can't I just get this out? Okay, so I can have this now. Right. So Midjourney helps with digital artwork, movie concept art, character design, book illustrations, advertising, fashion design, interior design, architectural visualization. We've seen all of this in painting and out painting for stable diffusion. Then we have other applications. Beyond digital art, diffusion models are increasingly used for medical image synthesis, scientific visualization, drug discovery, image restoration, super resolution, video generation, 3D assets generation, and game development. So, example, suppose the user enters the prompt, a majestic lion wearing a golden crown painted in Renaissance style. Okay, so this is an example right here. So I think I want to implement that. Uh, so I just post it here, paste it, and run. So we'll be waiting for that image. So, but as we wait, let's go. So the first thing that is happening there, you encode the prompt. So as I tap that prompt now, we know ChatGPT doesn't understand English, so it has to encode it. It has to break it down into tokens and give it token IDs and do the embedding in terms of vectors. So the text encoder convert the prompt into numerical embedding that captures its meaning. Then number two, generate the random noise. So the first thing you see everything goes, you can't see anything, so you see noise all over the place. So generation begins with random latent noise, ZT, which is noisy. At this stage, there's no recognizable image. So when it starts first, you don't see any recognizable image. All right. And then at the end of the day, you have iterative denoising. So the unit repeatedly predict the noise present in the latent representation. After each prediction, a small amount of noise is removed. Then the latent representation gradually changes from random noise to rough shapes to lion silhouette, detailed lion, and final artwork, and which you then see. So you can now see the lion right here now. So you see the lion, majestic. So a majestic lion wearing a golden crown, painted in Renaissance style. So you see that right here. Then so yeah, it applies classifier-free guidance. So the text embeddings continuously guide the denoising process so that the generated image matches the user prompt. So the lion gradually acquires a golden crown, Renaissance painting style, realistic fur, as you can see. So it has realistic fur. Then the dramatic lighting. Okay, you have dramatic lighting. You can see the lighting. Then artistic textures too. You can see all of that. Then you have decode the latent representation. So finally, the variational autoencoder decoder converts the cleaner latent representation to a full resolution image. So the result is a realistic AI generated Renaissance painting of the crowned lion, as you can see right here. So here we see progressive noise visualization. So this next set of images you're going to see show us progressive noise visualization. So we have an image that is 128 by 128, and then the image itself is 4090 equals 1. And then we have the axis 1, 5. Then we have noise levels, no noise, 0. Then noise level 0 0.2, 0 0.4 to 0 0.8. And then we have all the axes in place and we plot. So in this case, we have, so you can see this is noise level 0. This is the sharp image. So at this level, you have more noise. So you have more noise, and this is noise level 0 0.2. Then here, noise level 0 0.4. So it's getting blurrier. 0 0.6 getting blurrier. And 0 0.8, by the time you get to 0 0.8, it's more like all noise. So you can hardly decipher the image. So what happens in the generation process like that is you have the noise. So the process forward is what is called the forward diffusion. And the process of recovering the original image back is what is called the reverse diffusion. And that is the standard procedure for generative how for text to image generation in most AI. So the key takeaways we have here are as follows. Diffusion models generate images by learning to reverse a gradual noising process. So during training, Gaussian noise is progressively added to clean images. Then during generation, a neural network repeatedly predicts and removes that noise. Then the forward process converts images into random noise, while the reverse process reconstructs meaningful images, right? So Stable Diffusion performs denoising in a compressed latent space, making generation computationally efficient. Then the unit predicts the noise, while the VAE converts latent representations back into full resolution images. Then classifier-free guidance helps the generated image closely follow classifier-free guidance helps the generated image closely follow the user's text prompts, So it's more like you have some false, you have some part of it following the prompt, some not follow, and then you have a balance at the end of the day, so you can get a proper image. Then modern AI systems such as Stable Diffusion and Midjourney are built upon these diffusion principles, enabling the creation of highly realistic and creative artwork from simple text descriptions. So that leads us to our practice problems. We've seen a lot about how AI converts noise into art. We've seen all of that. Um, so here I'm going to answer two questions, but for the first part, I'll just read out the answers. So I'll be answering questions 9 and 16. So question 9 is more like theory. So instead of taking time to write down, I'll just say it by mouth. I'll try to be slow as much as possible. Then there's another one that involves calculation. I'll just do that one, and then we'll call it a date with this. So see the problems. Now you can see problems. You can see problems 1 to 3 clearly here. So like I said, I'm solving 9 and 16. 1 to 3 can be seen here. Then you can see all of 4. You can see 4 and 5 can be clearly seen here. 4 and 5. Then 6. You can see 6 to 9 here. So I'll be dealing with 9. Explain why Stable Diffusion performs diffusion in latent space rather than directly on pixel values. So I'll just talk about that verbally, Then you can see questions 10 to, can we say 10 to 13? Okay, you can see questions 10 to 12. Then 13, you can see questions 13 to 15. Then question 16, I'll be taking care of 16. It's a numerical problem. Suppose beta is 0.25. The clean image pixel has value x naught equals 0.8, and the sampled Gaussian noise is epsilon equals 0.6. Using x1 equals square root of 1 minus beta x naught plus square root of beta epsilon, compute the noisy pixel value. So we're going to deal with that. Then you have you can see question 17 okay, from here 17 to 19. Then 20. Okay, so let's go and deal with this as we try to bring this home. So we have problem 9. Problem 9 says explain why stable diffusion performs performs diffusion in latent space rather than rather than directly on pixel values, directly on pixel values like that. Okay. So so I'll just talk. So of course the solution will be this. A high resolution image may contain millions of pixels, as we know. So if diffusions were performed directly on these pixels, the neural network would have to process an enormous amount of data doing every denoising step, right? So for example, if you have a 1000 by 1000, a 1024 by 1024 RGB images, that is 1024 by 1024. I'm talking about the solution now, by the way. Okay, I thought I'd change that. So suppose you have a 1024 by 1024 RGB image. So that will contain so since it's RGB now, talking about color, right? So you have 1024 by 1024 multiplied by 3, which is 3,145,728. So pixel values. So performing hundreds of denoising steps on more than 3 million values would require a tremendous amount of memory and computation. So Stable Diffusion solves this problem by first compressing the image into a much smaller latent representation using a variational autoencoder VAE. The diffusion process is then performed in this compressed latent space. So the advantages are much lower memory usage, faster image generation, reduced computational cost. So these are some advantages of using variational autoencoders like that. So we then see that the diffusion process is then performed in this compressed latent space. So the advantages are much lower memory usage, faster image generation, reduced computational cost, ability to generate high resolution images on consumer GPUs, then preservation of information, important visual features while discarding unnecessary pixel level redundancy. Then after the denoising is complete, the VAE encoder converts the latent representation back into a full resolution image. So the key idea is that okay, I guess I can write this now. So the key idea, in answering that question is this. So like I said, the key idea there is this. Stable diffusion works in latent space, in latent space because because it is it is far more computationally efficient, far more computationally efficient than working directly, than working directly with millions of image pixels, millions of image pixels, while still while still preserving while still preserving enough enough information to 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 reconstruct realistic, high quality images. All right, so we move on to the other question. So problem 16 now. Problem 16. Suppose beta is 0.25. The clean image pixel is x naught equals 0.8, and the sampled Gaussian noise is epsilon equals 0.6. Using x1 equals square root of 1 minus beta x naught plus square root of beta epsilon, compute the noisy pixel value. Okay, that's straightforward for sure. So we have the solution. So, I mean, I'll just go straight. So we have x1 to be equal to square root of 1 minus beta. Beta is 0.25. So that's 0.25 multiplied by, what's that now? X naught. X naught is 0.8. You have 0.8 here. Plus square root of beta, that's square root of 0.25 multiplied by epsilon. Epsilon is 0.6 from what we have up here. So we just put this into the formula and we're good. So x1 is square root of 1 minus 0.5 is 0.75. That multiplied by 0.8 plus square root of 0.25 times 0.6. So x1 is equal to square root of 0.25 is 0.8660 into 0.8 like this, plus square root of 0.25 is 0.5 multiplied by 0.6. So x1 is then 0.8660 multiplied by 0.8. That is 0.6928. Then this is 0.3 right here. So that means that x 0.300. So x1 is simply 0.9928. So therefore that's what we have there. So the final answer, x1 is 0.9928. So the added Gaussian noise has increased the pixel value from 0.8. So we can conclude with that, right? So the added Gaussian noise, has increased the pixel value from 0.8 to approximately 0.993, making it slightly brighter and noisier. So that's how that works. All right, so that is how we come to the end of this, how AI turns noise into art. So I'll flash the questions once again so you can try your hands on this. So here you have questions. Should be able to have questions 1 to 4. Yeah, all of questions 1 to 4 are here now. Then all of questions 5 to 9 are here now. Then questions 10 to 13 all here. Questions 10 to 13. Then 14 to 16. and 17 to, you can see 17 to 19 here, and finally 20. All right, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to my channel already, I thank you very much for doing that. If you haven't subscribed, this is a good time to do that. Just go ahead and subscribe, and you can hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you special privileges, gives you special privileges that you find out as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.